Good morning and welcome to today's webcast, How Chemical Tracers Can Reduce Costs, Boost Production, and Guide Adaptive Strategies in a Rapidly Changing Oilfield Market. I'm Cameron Wallace, Digital Editor of World Oil, and I will be your moderator today. With oil prices hitting decade lows and energy activities downsized during a global pandemic, operators globally are seeking assurance that every spend drives a strong return on investment. Yet many completion and production choices are made in an environment of uncertainty, making technology that can inform well design and operational planning more crucial than ever. Chemical tracers are one such tool. A proven and reliable method of reservoir surveillance, tracer studies have demonstrable value for quickly and accurately adapting field strategies to real-time market needs. Whether a conventional or unconventional field, a properly designed and utilized tracer study has the potential to reduce lifting costs, improve production, and mitigate risk to CAPEX and OPEX spends. Joining us today are Mona Lisa Chatterjee, Consultant in Reservoir Engineering, Patrick Hayes, Business Development Manager of North America, and Dr. Sudipta Banerjee, Global Technology Manager from TracerCo. Mona Lisa Chatterjee is a reservoir engineer with TracerCo Limited, Abu Dhabi. As a technical consultant, she manages reservoir studies across the GCC, Russia, and Caspian. Her main responsibilities include quantitative and qualitative analysis of the tracer data for a wide range of reservoir access across the regions, assisting clients in understanding fluid flow dynamics. Prior to joining TracerCo, she worked with the Indian National Oil Company, ONGC, where she managed drilling, well intervention, and production activities. She's also worked in areas of well test analysis, EOR laboratory studies, and reservoir simulation. She's authored 12 technical papers across the discipline of reservoir engineering and tracer technology. She holds an MS degree in chemistry from IIT Dhanbad and currently is completing her dissertation for an MBA on Sales and Marketing Interface from the University of Wolverhampton in the UK. Patrick Hayes has 15 years with TracerCo, performing various operational and managed roles in the upstream and downstream areas. Patrick worked with the upstream, midstream, and downstream businesses to enhance clients' production and help with gaining efficiencies. While working for TracerCo overseas, Patrick was responsible for the operations and management of the projects performed in the North Sea, Europe, Middle East, and parts of West Africa. Finally, Dr. Sudipta Banerjee is the Global Technology Manager at TracerCo, where he is responsible for the reservoir tracer technology portfolio, creating and launching new technologies that deliver on the business unit's short-term and long-term strategies and addressing operators' needs. With over 15 years in the oil field, Sudipta has global work experience in locales ranging from Alaska to Saudi Arabia, implementing technical solutions in enhanced oil recovery and hydraulic fracturing operations. He also has multiple patents, awards, and conference papers to his name, and lectures on well design as part of the Society of Petroleum Engineering short course program. And then before we get started, I just want to review some general housekeeping notes. Following the presentation, we will have a short question and answer session. There you can participate in a Q&A session during the presentation by typing your question into the Q&A box located on the bottom left corner of your screen and then clicking the Submit button. You may enlarge the slide window at any time by clicking on the arrows on the top right corner of the slide area. The slides will advance automatically throughout the event. If you're experiencing problems with the program, please press F5 on your keyboard to refresh the presentation. You can also visit the webcast help guide by clicking on the Help button below the slide window. And with that, let's get started. Dr. Banerjee, the floor is yours.
Thank you. As Cameron mentioned, my name is Sudipta Banerjee, and I'm the first of today's presenters. Over the course of this webinar, we hope to lead you through a greater understanding of tracer technology and demonstrate how this diagnostic tool has been used across the globe to understand reservoir behavior and optimize well development strategies. So to achieve this, we'll be sharing some case studies in which various forms of tracers were used to measure production, inflow behavior, capture interwell communication, and evaluate a hydraulically fractured shale oil play. Now, before we actually get into the detailed case histories, I feel it's important to provide this foundational knowledge of how chemical tracers work and what they are. At their core, tracers are actually a very simple idea. They are markers. They are fluid markers that allow an engineer to track the behavior and movement of oil, water, gas, or some combination of those in the reservoir and through the well itself. Yet for such a simple idea, it's proven incredibly powerful as a visualization and diagnostic tool, especially in complicated reservoirs, because it provides this accurate reflection of how a well's completion and production are interacting with the reservoir in a way that mathematical models and simulation can only approximate. Now, many things can serve as tracers. Radioactive isotopes, for example, were some of the first interwell tracers, and more recently, things as varied as DNA fragments and RFID tags have been sold in a class of unconventional tracers. But today's conversation is going to focus predominantly on three variants of chemical tracers in the form of liquid tracers, solid particulate tracers, and polymer-enclosed tracers. Now, why have we focused on these three forms of chemical tracer delivery? Mostly because things that are sold as a tracer are not necessarily good tracers. And the selection of an effective tracer is critical to having a usable tracer study. On this slide, I've tried to list out qualities that I feel define what is a good tracer, and things that basically ensure that you can avoid an incorrect interpretation of tracer data. Right off the bat, one of the most basic things that define a good tracer is that the tracer itself doesn't degrade. You don't want it to degrade during injection, production. You don't want it to degrade in the reservoir. You don't want it to be something that's reactive with other elements it might come in contact with. And this is a legitimate problem where many chemicals will actually interact. There's been issues with biological tracers, for example, degrading either due to thermal issues or being consumed by in situ bacteria. These are things that will generally make a tracer unsuitable for long-term studies. A second, and again, seemingly obvious requirement, is that the tracer not be absorbed by reservoir rock, by proppant, by other materials. Generally speaking, when we're interpreting tracer data, we're dependent on the ability of it to freely flow along with whatever fluid it's measuring. And so when tracer kind of leaves or enters your system because it's being absorbed and released, that will skew your data set. Also important is that 95% of the time, you want a tracer that isn't partitioning, basically that it isn't soluble in multiple fluid sets. We generally want a tracer to mark a specific phase. Now, partitioning tracers, ones that are soluble in multiple phases like oil and water, tend to skew our ability to mark and measure the flow of a given phase. So we generally want non-partitioning tracers. There are going to be some exceptions to this, and in fact, one of our case studies addresses it. But generally, we want an oil tracer to be soluble and measure oil. We want a water tracer to be soluble in and measure only water. We want a gas tracer to be soluble in and measure only gas in order to quantify and distinguish the respective behavior. We, of course, want our tracers to not skew the system that we're measuring. So we don't actually want it to influence the reservoir fluid itself. So if the chemical you're using as a tracer ends up behaving like a friction reducer or a stimulating fluid, then now you're measuring behavior that isn't representative of your actual reservoir fluid at large. And that's going to skew the data that you're trying to collect. Again, there are some exceptions to this rule, but generally, you don't want your tracer to be something that is naturally present in your reservoir. If it is naturally present, it's now harder to basically trace what you've introduced to the system, and you tend to create a lot of background noise that hides the tracer behavior that you're trying to measure. Tracers should be easily detectable. So using common analytical techniques like mass spec or GCMS, you really want something that can be measured at low concentrations and done relatively quickly. A lot of the value in tracer studies is really in that ability to get sort of a real-time understanding of what a reservoir is doing. So if the analytical method is difficult to use or takes a very long time for you to get results back from, that tends to undermine the value of the tracer study itself. Tracers should be, ideally, either non-toxic or a very acceptable and low level of toxicity. I already mentioned that radioactive tracers used to be in vogue. While they met most of the requirements on this list, radioactive materials are obviously difficult to store, to use, to transport, which is why they've been displaced by other options. We are stewards and neighbors of the environment and members of community. So the things that we use to analyze the reservoirs, ideally, should not be things that can bioaccumulate or cause any harm to the environment at large. Finally, you want tracers that are commercially viable. So we want something that can be purchased in large quantities, so we can use them over a number of different wells and without long lead times, and something that is achievable at a very reasonable cost. For this reason, for this list of reasons, we tend to focus on chemical tracers that tend to fall into three major categories. Now, let's start with liquid chemical tracers, sort of the first big category. Liquid chemical tracers, as the name describes, are tracers that are delivered in a liquid form. They are generally very easy to use. They are not terribly complex. And they're going to be used in wells where it's possible to inject that tracer into your well, into your reservoir. So they tend to be used very commonly in hydraulically fractured wells where you're injecting a stimulation fluid, and in interwell studies where you have wells that are either going to be on injection for a period of time or are dedicated injection wells. For fracked wells, they tend to be added directly to the frac fluid of each stage, like any other liquid additive. Liquid water tracers and liquid oil tracers are the most common, though liquid gas tracers do exist and are becoming more prevalent in the industry. Before we kind of move on, I just want to address one possible point of confusion, because just a few slides ago, I was talking about how you want non-partitioning tracers, tracers that tend to remain in a given phase. And when I talk about adding oil tracers, this oftentimes is a point of confusion because most frac fluids are going to be water-based. So how do you add an oil tracer that should ideally only be soluble in oil and not in water to a water-based system? Well, the answer is that an effective oil tracer isn't truly miscible in, say, a slick water. Instead, it's actually just displaced by it. The liquid oil tracer is usually quite hydrophobic, and upon addition to the frac fluid, is generally dispersed on the outside of that sort of bolus of fluid as it's being pumped into the reservoir. Once the fluid breaks the reservoir rock and comes in contact with in situ hydrocarbon, that oil tracer, because of its desire to be in an oil phase, jumps, in essence, from your frac fluid into the oil it preferentially wants to be in. Once it's actually in the oil phase, now it proceeds to mix and diffuse with all the oil that is in contact, effectively marking that oil that is within the localized drainage area. Likewise, the liquid water tracer that you may have added to a frac fluid is mixing with and marking all the water that you have injected with your stimulation fluid, and is now mixing and diffusing with any in situ water that comes in contact with. Once the tracer has been applied, we wait for the well to go in production. Once it's gone in production, we proceed to start capturing samples at surface to analyze how much of the applied tracers have returned. We're essentially treating this as a mass balance problem, where the recoverable oil, water, and gas in your well's drainage area is sort of our fixed volume. So as we measure the amount of tracer that has been applied and returned and the amount of oil, water, and gas that has been produced, we're able to use that mass balance to now assign produced fluids to each zone that's been treated with a unique tracer. So if every stage of a fracked well has a unique oil and water tracer, we get, in essence, a production log showing how much is being produced from each stage and how that production is changing over time until all of the injected tracers recovered. We get something similar to the image on this graph, where the dark blue lines kind of indicate the cumulative production from a given stage. And behind it, we can actually see, based on the changing tracer response at each sample point, how production is changing over time. Now, this can be exceptionally valuable data. For a producing well, it can demonstrate how the well is interacting with its reservoir as you change operational conditions. So if you're changing your choke, if you're changing your production rate, this gives you an idea of how that's actually affecting production along your lateral. It also gives you a way of quantifying production and comparing different completion designs. So as you start changing your stimulation strategy from one well to another, here's a way to sort of see how that is actually affecting you on a stage-by-stage basis. In examples where you're also measuring production at offset wells, it can determine whether cross-communication exists and to what extent. And in doing so, it gives you this very immediate, highly accurate insight into what your well is truly doing. Now, solid particulate tracers are a second class of tracers to discuss. And this is another technology that is oftentimes used in hydraulically fractured wells. The big difference is that information from these solid particulate tracers is a very qualitative response of flow versus a quantitative response. And that comes down to how the tracer is actually affecting your fluid. So with liquid tracers, we are directly adding tracers to our oil, water, and gas, ideally marking all of it. With solid particulate tracers, we have an intermediary, a carrier material, something that usually is proppant-like, but is also inert and has a lot of available porous spaces, things like activated charcoal. Now, in advance of the job, you will take something like activated charcoal, you will soak it in your actual tracer, and your tracer now gets absorbed into those porous spaces. And now when you're pumping a frac job, you can add this material to the blender as you are, adding proppant to your frac stream. And now it all gets mixed up, pumped away, and you now have some of these solid particulates that have been infused with tracers lodged within your proppant pack. Now, the reason why this data is qualitative versus quantitative is because you have skewed your mass balance with an additional sort of variable interface, which is how quickly is tracer actually being released from this carrier material. And the rate of tracer release ends up being very dependent on a number of different variables, everything from your downhole temperature to any sort of chemical interaction between your tracer and the carrier material to available surface area and how much that surface area is actually getting wetted by the appropriate phase. This is something you can't generally consistently replicate from well to well or tracer type to tracer type. And it's something you can't really predict particularly well as you're applying it. So not knowing how much tracer is actually available for any given time step to mark fluids makes it very difficult to quantify. The other big issue is how much of this solid particulate generally gets used. If you look at some of the published literature in SPE and other industry groups, you'll find that solid particulate tracers are usually a low-cost solution, and so a very small amount of it actually gets used. At HFTC early this year, one vendor was talking about how, regardless of stage size, they apply 8.8 pounds of solid particulate tracer to mark fluid flow. Now, in my example on this slide, I've got a frac stage where we're pumping 380,000 pounds of proppant, which is normal for like the scoop stack, so Oklahoma, North Texas. For that size of a frac stage, 8.8 pounds is 0.02% of that proppant pack volume. To visualize that, I've got 100,000 dots on this slide. 2 of them are red, indicating the 0.02% that are actually solid particulate tracers. If you were looking at this image with the naked eye, you'd probably think that there was 0 tracer actually present. But when you blow up a square of about 100 dots, you can see those 2 red dots. This is important because when you have a very small amount of tracer present, you have the ability for localized flow to basically bypass your tracer. I mean, consider all the different things that might cause localized flow to be different from representative flow. You could have emulsified flow. You could have phase slippage. You could have localized proppant pack damage. All these scenarios may cause the embedded tracer to never see the right phase and never release the tracers that are supposed to mark it. As a result, you miss out on that ability to truly quantify flow. Now, where I would argue that this technology shines is when you're trying to get a binary response for flow, when you're just trying to basically measure has water flow or oil flow occurred. So if you're looking to see if your zonal isolation is holding up, if you're just trying to get an idea if water breakthrough has occurred and not necessarily how much water breakthrough there is, here's a very effective and expensive technology to do that. The final chemical tracer I'm going to cover is polymer-enclosed tracers, which on the surface seems very similar to those solid particulate tracers. Here, the tracer is enclosed in a polymer matrix from which it diffuses out of into the phase it's supposed to mark. The polymer can be shaped into whatever form you need, usually bars or rods, and can be installed within the completion. So wells where you can't inject a liquid tracer, you will oftentimes use this type of tracer, with the tracer installed either in tracer carriers that are added like pup joints to your completion, or where the polymer is actually installed within the drainage layer of the sand screen itself, like in these images. Now, there are another number of misconceptions when dealing with these polymer-enclosed tracers that I'd like to clear up really quickly. One of the first ones is how the tracer is released. A lot of people envision this as sort of a flow-related erosion of the tracer bar. They envision something like how a bar of soap is dissolved by water flowing over it. In truth, the polymer is this matrix, and the tracer diffuses out of that matrix at a fixed rate. You're not actually wearing away the bar. It doesn't disappear. The second misconception is actually kind of related to the first one, which is that if you're seeing a higher measured concentration of your tracer at the surface, it means you have a high flow rate from that zone. Now, this would make sense with that erosion-based understanding of how it works. You know, again, if I had a bar of soap and I'm flowing water over it very, very quickly, I would expect that soap to erode away faster and there to be more soap in my fluid stream. But when we talk about diffusion, and we talk about diffusion at a consistent set rate, high flow rates actually dilute your available tracer. And so you have the opposite response. If you see a high concentration at surface, it suggests a low flow rate from that segment because you have less dilution. The final misconception is that these polymer-enclosed tracers are a quantifiable way of measuring flow across your lateral throughout the life of the well. And that is partially true. Now, even though we've kind of made that release rate from the polymer matrix consistent, unlike with the solid particulate method, you still have issues with a mass balance that make it very difficult for you to quantify flow during steady state production over the life of the well. However, this is a technology that can capture and quantify flow from different zones when you're going from a period of sort of stagnation and startup production. So if your well has been shut in for a period and you bring it online, you will get an immediate snapshot image of how flow is sort of distributed across your wellbore in a quantifiable way. When the well has been producing for a while, when you don't have that transition period, you get a qualitative understanding, but not a quantitative understanding. Let me explain how that works. So here we have an example that kind of walks us through one of the classic methods of interpreting polymer tracer data. We have a well where different polymer-encased oil tracers are being used to mark 6 different zones. While static, these polymer-enclosed tracers are now diffusing out tracer to mark the oil in the near wellbore area, kind of creating a localized cloud of tracer near the sand control screen. When production starts up from the well, that cloud of tracer gets sucked into your production tubing, and you end up having this bolus of tracer now traveling up the well to your sampling point. Now, since we know the completion design of this well, we know the capacity of your production tubing, we know the inner diameter of your production string, and so if we know that there's, say, 100 barrels of capacity from the beginning of that first tracer segment to surface, and it takes 10 minutes to clear that capacity from the well and get the first bit of tracer from that localized tracer cloud, we now know that flow averages from that point at 10 barrels a minute. By basically looking at the difference in arrival times for the different tracers, we can now establish the flow rates from those different segments. In an ideal world, you'll see a tracer response that kind of looks like this. You know, real clear tracer responses, defined arrival times, and as a result, very easy quantification. In the real world, you often see muddier responses, something that requires more expertise to correctly interpret, with extended or even non-existent tracer returns, making quantification a little bit more difficult. When you have these sort of non-ideal tracer data, that's where working with an experienced partner becomes more important in terms of establishing what the arrival time actually is and what the flow is for different zones. Now on this slide, we actually have a worked example, a simple case where you can take arrival times and now do the math to figure out what the flow contribution is from different zones. In the interest of time, we can't really go through this step by step, but since we have the advantage of this being a recorded presentation, I invite you to come back later and kind of look at the slide and work through it independently to get an idea of how a sort of pulse velocity method is used to quantify flow. But I also hope that you'll accept that during that transition, from stagnant to production, tracer responses from polymer-enclosed tracers allow an operator to quantify flow. With that introductory background on liquid, solid particulate, and polymer tracers, let's now see how operators have used that data to drive their field and well decision making. With that, I'm going to turn things over to Mona Lisa.
Thank you, Sudipta, for the very informative introduction to these chemical tracers. A very good morning, afternoon, evening to all of you, wherever you are. So moving ahead, let me take you through two very interesting and recent case studies that demonstrate the use of these chemical tracers as reliable and cost-effective way to understand reservoir and well flow dynamics, aiding to reduce key uncertainties. The two case studies that I would discuss here are both novel in their regions of applications. The first one relates to a sandstone reservoir at an onshore field in the Sultanate of Oman, and the second case study pertains to a relatively new oil field situated about 80 kilometers off the coast of Abu Dhabi in the United Arab Emirates. A southern field in Oman was identified to be a good candidate for an alkali surfactant polymer or ASP plug as a tertiary mechanism of oil recovery for its sandstone reservoir. As we all know that for any EOR application, the incremental oil recovery must be estimated first at a core level and then through a pilot study before being implemented at a full field scale. Interval oil saturation estimation using passive and partitioning tracers is the sole technology that offers saturation measurements at an interval scale. Now, we initiated this study with the following key questions. Now, what is the fluid flow distribution within my pilot? What is the interval remaining oil saturation prior to ASP application? How effective is my ASP formulation? And what could be the incremental oil gain after ASP? The study was carried out over 3 years across 4 phases, each phase with a distinct set of objectives. At the beginning of the study, it was important for us to understand the existing fluid flow dynamics and injection balance of the studied area. Phase 1 conformance study was initiated in year 1 at the beginning of the water flood with the primary objective of studying virgin streamlines, reservoir connectivities, and fluid flow dynamics. Phase 2, that is pre-ASP conformance study, was carried out post 1 year of water flood to establish the stability of the streamlines. Now, later in the presentation, we will learn that this is a prerequisite for oil saturation measurements using partitioning tracers. Phase 3, initiated after 2 years, targeted measuring the pre-ASP remaining oil saturation within the pilot. And finally, phase 4, and the most important of all phases, measured the effectiveness of the EOR by mapping the incremental oil desaturation. Now, this slide shows you the pilot layouts for the study. As you can see from the plot, there is a central injector, I1, in the middle of an inverted 5-spot pattern, 4 pilot producers, P1, P2, P3, and P4, and there are a few other offset wells. In the first phase study, 1 passive tracer was injected in the central injector, and the 4 pilot producers, along with some offset producers, were sampled for tracer breakthrough. During phase 2, the same process was repeated, however, this time with a different passive tracer to avoid any interference of the tracer signals. During phase 3, another new passive tracer and 2 partitioning tracers were injected in the central injector. And finally, during phase 4, the 4th unique passive tracer and the same 2 partitioning tracers were injected in I1. While 4 unique passive tracers were used across 4 phases, the same 2 partitioning tracers were repeated for phase 3 and phase 4 to reduce the number of variables in the study. Now, before we get into the actual results for this study, let me give you a brief overview of what to expect out of a classic passive tracer interval study. In our case, that is phase 1 and phase 2 here, and how we can use those results for production and cost optimization. The output data can be interpreted both in a qualitative and quantitative fashion. While the qualitative output can range from information like well-to-well connectivity, delineation of streamlines in the reservoir, fault block communications, and detection of high permeability channels, quantitative results are extracted through age distribution function analysis. This provides important and deeper insights of the reservoir by quantifying values of swept volume, dispersion, Lorentz coefficient, sweep efficiency, and injection mass balance. And we all know that these physical numbers are of invaluable importance to oil field engineers to manage their reservoirs in the most techno-economically optimized fashion. So what do we get to see as a final output of a passive interval tracer study? That is your top curve on the left, a typical concentration versus time curve. Although it seems like a very simple curve, a closer insight reveals a wealth of information about the strength of connectivities between the injector and producer, the number of contributing layers, the nature of the flood front movement. This concentration versus time curve is then subjected to age distribution function analysis that produces the curve on your top right. That is commonly referred to as an age distribution function or the ET curve, which is essentially a normalized concentration curve. Now, converting this concentration function to age distribution function has several advantages. First, this places all the curves for analysis on equal footing for comparison. As also, normalization of the output signal accommodates treating the input function as direct delta function required for deconvolution of the tracer signals if needed. Extrapolation of the ET function offers a quick means of evaluating the flow system, which means that the study need not be continued for a longer duration, hence saving cost. Now, once a complete tracer curve is obtained by normalization, interpolation, and further extrapolation, that can be used to plot complexity curves like the one you see on your bottom left. Now, this storage versus flow capacity plot is a direct indicator of reservoir complexity. A completely homogeneous system would have an ideal straight line plot like you see the red dotted line there, now signifying a 50% flow happening through 50% of the available pore volume. Now, the further the curve moves away from linearity, higher is the reservoir complexity. Now, in most times, these information is only available at core level or at max log level, but tracer studies offers a direct estimation at a field level. The curve on the bottom right is a sweep efficiency plot which signifies how quickly or slowly the contacted pore volume between an injector and a producer is being swept. The outcomes are more detailed. However, what I discuss here offers you a quick understanding of the tracer results. Now, after having an idea of what to expect out of a result, let us now move to discuss the actual results from all these phases. As we discussed earlier, the tracer results from phase 1 and phase 2 were subjected to age distribution function analysis, and the resultant curves from all the 4 pilot producers are shown on this slide. Now, further to this, we will explore how to interpret these curves in terms of quantitative values. Now, this slide summarizes the quantitative results from phase 1 and phase 2. Now, what are we looking for here are similarity in trends and values. Now, if we can find the similarities in values and trends of the same, we can then come to a conclusion that our water flood has matured, which means there would be essentially no mobile oil within the reservoir, and the pilot is now ready to enter the first phase of oil saturation measurement. If you see from the values, a close match on the phase 1 and phase 2 conformance confirms established streamlines and a mature water flood. Now, by this time, you might have heard me use the term like passive and partitioning traces quite a lot. Here is where I elaborate what they are and how they work in synchronicity to estimate the oil saturation at an interval level. A passive tracer, as the name suggests, is inert in nature. Once injected in the reservoir, these tracers flow along the injected fluid and do not interact with any other phase within the reservoir. However, partitioning tracers have been imparted with a special property of selectively partitioning between the injected phase as well as other phases in the reservoir. In this case, the partitioning tracers injected with the water phase would selectively partition in the oil phase whenever it encounters the same. And remember, we have already established a mature water flood with no mobile oil. Now, this means that the partitioning tracers are immobile within the immobile oil phase, and they do not move at that time. However, when these tracers sense water phase again, it quickly reverts to the water phase and continues its journey to the producer. Now, due to this constant back and forth movement, these partitioning tracers then get delayed at arrival at the producer as compared to the passive tracers, which do not interact with the oil phase and moves without any delay. Now, if you look at the plot, you can clearly see the arrival of the passive tracer much earlier than the partitioning one. Now, this delay in time of peak arrival of the passive and the partitioning tracers, along with the laboratory-generated partitioning coefficient or the K values, is then used to estimate the interval oil saturation. Phase 3 results, that is estimation of the oil saturation prior to ASP deployment, is presented in this slide. In phase 3, we injected 1 unique passive tracer and 2 unique partitioning tracers to estimate the interval oil saturation. Now, while use of 1 partitioning tracer is usually enough, however, using 2 partitioning tracers gives us better statistical validation. In the plot, you can clearly see that the blue plot for the passive tracer that arrive earlier than the red and the green colored plot for the partitioning tracers. Now, these plots are denormalized and subjected to beta matching techniques to arrive at the oil saturation estimation. An average oil saturation in the directions of P1, P2, and P3 were found to be between 36 to 37%. No analysis could be done for the direction of P4 due to the presence of a pole and hence no tracer response. Between phase 3 and phase 4, the ASP flood was carried out, and phase 4 tracer study revealed the final outcome of the tracer study, that is estimation of the incremental oil gain from the ASP flood. Similar to phase 3, the fourth unique passive tracer was injected in the central injector I1, and the same two partitioning tracers were used again. The resultant passive and partitioning tracer curves were normalized and subjected to beta matching to generate the final incremental oil gain values, which is simply the difference in oil saturation between phase 3 and phase 4. The tracer results showed a considerable reduction in oil saturation from 36 to 37% to 0 to 2% within the water flood contacted pore volume. The incremental oil desaturation by ASP determined through the tracer study was also in line with the results obtained from NMR saturation studies in an observation well. Now, very interesting to note here that the resultant saturation of 0%. Now, this is to be kept in mind that while the actual resulting oil saturation can never be 0, these results are from the desaturation within the contacted pore volume. Now, this was a joint paper with Petroleum Development Oman, and we presented that as a P192649MS, and should you wish to make a note of that. Now, coming to the second case study that I talked about, now that we have discussed the tracer studies using the reservoir characterization, let us now move on to understand how we can make use of these tracers for fluid flow monitoring and phase quantification at a well level. That too, for a prolonged period of time with zero well intervention and substantially low cost. The tracers used here are very different from the one used in the interval studies, and these tracers are popularly known as inflow tracers or intelligent tracers. Now let us now find out how they can help you. Al-Yasab Petroleum, along with ADNOC Offshore, is jointly developing a cluster of marginal green fields in offshore Abu Dhabi, deploying horizontal wells with water injection support. The challenge was to keep the development cost low without jeopardizing the reservoir health and ultimate recovery, while meeting corporate commitments on production. The lifecycle development cost of these fields is among the highest in the ADNOC group due to relatively small developable reserves and high cost of offshore operations. The field is in a water depth of 82 feet and is being developed using 13 horizontal wells, including 5 peripheral injectors. Recently, the field was brought on stream. Inflow tracer technology was piloted in one of the wells and is planned to be deployed in all the horizontal producers in the coming future. We initiated the study with the following key questions. Now, what are the zones that are contributing to the flow? Now, which zones are my source of oil and water? And was the well cleanup complete? Unlike conventional passive tracers used in interval studies that flow inertly along with the injected fluid, these tracers are integrated within the lower completion of the well and can remain dormant for years until they are contacted by the target fluid phase. As water or oil phase contacts the target tracer, it diffuses and flows from the polymer and into the production stream. Once triggered, these tracers continue to release slowly. Wellhead fluid samples are collected from time to time and analyzed in the laboratory to detect tracers and identify zonal contributions. The figure shows the release profile examples of two tracer polymer combinations. High initial rates of tracer A is due to the exposure of full surface area to the tracer to the target fluid. In addition, if you see, tracer area declines much sharper, suggesting higher fluid flow rates from the corresponding zone relative to tracer B. However, over time, the tracer release rate reduces to a steady amount as tracer diffuses from within the polymer structure. Thus, higher rate wells will have a lower tracer concentration than lower rate wells as production continues. Once the zone begins to produce water, surface area of the polymer will now become occupied by that fluid, and therefore the total release of oil tracer will now decrease, while its detection of water tracer will be detected in surface water. As a recent development, microencapsulation of these tracers has been brought about, a technique that helps control release rate to a greater extent, thus making fluid flow profiling feasible even with longer periods of time with lower cost implication to the client company. Now, to answer some popular questions, these tracers remain unaffected from stimulation acid, completion fluid, impurities, and salinity. So how do we design an inflow tracer project? First, the tracer mass is calculated that is required to provide us with a desired lifetime. Now, once that is established, the load completion and the logs are then studied carefully to integrate the tracer system in the best possible fashion. TracerCo in-house software flow tracks and estimates the time required for sampling, and finally, the inflow tracers are integrated within the system. This can be done in varied ways. In this case, this was a perforated liner and a packer system. However, screens, slotted liner, ICDs, ICVs, with or without tracer carriers are also equally attractive options. In this case, 18 inflow tracers, 9 oil and 9 water were allocated to these layers along the drain hole. An inflow tracer study is carried out in two stages, a transient state and a steady state. While a transient state is quantifying the zonal oil influx and relative water cut percentage, the steady state yields information on the zonal fluid contributions under stabilized flow. The transient state offers information on the possible potential of a zone, where a steady state confirms the sustainability of production from the zone over time. In the transient state, the well is shut in and the fluid in the wellbore generates a tracer cloud around the wellbore at each zone of interest. The well is then open to flow, and the tracer clouds now flow with the production stream, resulting in a decay of the tracer concentration that is directly proportional to your zonal inflow. The fluid flow contribution in a wellbore can be measured by understanding the pipe volumetric and the time by a tracer pulse to flow from one position to the other. Alternatively, comparative decay analysis is utilized to quantify the oil inflow in the transient state. In the steady state, this decay principle cannot be used as the well flows in equilibrium. Hence, quantification of oil inflow in the steady state is not possible. This slide presents inflow tracer results from the transient state study. As expected, the better quality layers A5, A7, A9 contributed most to the production. A portion of A7 sublayer, if you see, initially contributed the highest amount at 27%. However, layer-wise A5 contributed the most at 39%, followed by A7 at 35% and A9 at 39%, reflecting the initial flow potential for these layers. The heel layers A1 and A3, which are relatively thin and low permeability, also exhibited some initial flow potential. Flow variation between individual layers is largely governed by underlying reservoir geology, heterogeneity, and wellbore connectivity. Water tracer response was found to be substantial towards the toe section of the well. However, subsequent production data and steady-state samples did not support presence of water in the production stream. This is also corroborated by conventional PLC, where water holdup was detected in the toe region, but no flow was recorded during the production logging. Hence, the initial burst of water in the transient state is attributed to the idle drilling or completion fluid resident in the toe area due to inclined lateral at around 87 degrees, together with the relative difference in phase mobility and continued well cleanup. Now, alongside with the inflow tracer study, a PLC was also run in the well, and the results were tallied. Now, both the techniques confirm stable and sustainable flow in the mid to toe region from A5, A7, and A9 layers. Both the techniques detected water at the toe region of the horizontal. Both techniques identified poor flow potential at the heel regions A1 and A3. The inflow tracers reported an initial flow potential from the heel region, which then ceased to flow in the steady state. Now, based on the tracer results, a corrective action was taken, and these zones at the heels were then acid simulated, and they sustained flow, resulting in an otherwise lost opportunity for oil gain. Inflow tracers offered an additional information on intra-layer contributions, which were not detected in the PLC. Due to positioning of the probes against the packers, memory PLC could only detect the total contribution from the respective well segments, regardless of the intra-layer flow. Now, both techniques reported flow uncertainties and challenges from the toe area of the well. Similar to PLC, inflow tracers suggested no flow from the toe region corresponding to the last tracer, OT1. So what were the main cost benefits of using inflow tracers for flow quantification? First, no well intervention, so no deferred production. The technology consists of inflow tracers strategically deployed along the well completion, capable to detect, quantify, monitor phase breakthroughs. This information helps understand the zonal fluid flow contributions without requiring well intervention and production deferment. Cost savings and improved profitability. Compared to conventional production logging, inflow tracers offer similar information but at a significantly less cost. Cost savings are up to about 78% over 5 years, assuming annual production logging in a green field. For an offshore program, a typical cost savings was calculated to be about 10 million USD over a period of 5 years. Additionally, operations under simultaneous conditions or SIMOPS allowed reduced logistics and reduced HSE risks. Now, this paper was presented as SPE 193246MS, if you want to take a note of it. So now that we have learned how inflow tracers can help us understand well flow profiling over an extended period of time, let us now understand how they can also help us understand short-term stimulation recovery as well. Now, with that, I would hand over the presentation to my colleague, Patrick Hayes, for this. Patrick?
Thank you, Mona Lisa, for those interesting case studies. I'll be presenting a communication study using liquid molecular tracers to evaluate landing zone targets, completions designs, parent well protection from frac hits, and infield well spacing. As previously described by Sudipta, chemical tracers are a great evaluation tool for identifying areas and stages that are not or are producing oil, water, and gas phases. Bringing quantified phase production together with drilling, geology, and completion brings the further return on investment. These components are presented in the slide with production over time. The green bars moving up and down represent the daily production, and the translucent green bars are the production summary per stage. This helps us define areas of long-term production and the changes over time, unlike qualitative non-phase specific data provided by DNA analysis, particulates, or particle tracers. When evaluating multi-well pads, the quantification of phase production is critical to the understanding of multivariables and the relationships from well to well, operations order, and the reservoir characteristics. The slide presents two separate ways of looking at data, one as a potential and a second as a cumulative. These need to be considered when evaluating best practices. The quantified phase communication changes over time, and the percentage recovered per well are indicated in the purple plot below, while the gun barrel view shows another look at how fractures can communicate outwards and downwards. Of course, being able to tie in layers such as formation grids, landing targets, and all individual components into a 4D viewer provides the ability to look at several multivariables at once. As we investigate the case study, tying the changes and the wells position together played a large role in making critical changes. For example, diagnostic investigations, wells are chosen that would provide the best opportunity to gain the most representative data. The case study that is being presented was completed in the Anadarko Basin and has several goals and objectives. As part of the aggregate of the Mississippian, the Merrimack and the Woodford have changing thicknesses across the Oklahoma region. This causes well spacing and infield development to become more of a three-dimensional problem with multiple horizons. This can be observed in the map to the top left of the page. One goal was to identify the production differences in two slightly different landing targets. Stages were traced in two different targets, resulting in clear differences of higher production from the experimental zone, as shown in the TPL, tracer production log, in the center right of the page. The second and third goal we will present are around infill development, looking closer at child well spacing, completions design, and protecting parent wells. As a baseline, two pads were drilled in similar stacked configuration. Well spacing of the child wells on the pad were approximately 1,750 feet horizontally. The child well nearest to the parent well was landed 360 feet below the parent and 1,750 feet horizontally apart. As a mitigation measure to protect the parent was shut in and allowed to naturally build pressure from the formation. The results indicated the furthest child well communicated approximately 5% of the tracer applied to the child well 1A to the infield child well 2A. indicating that there was enough well spacing between the child wells. However, significant communication was observed from the child well 1A to the parent well above. Over 17% of the water tracer applied from the child well 1A was recovered from the parent well, demonstrating this well spacing to be insufficient. In the second pad, well spacing remained similar. However, the child wells were drilled in opposite directions of the parent well. In addition, the mitigation strategy had changed. The parent well was preloaded with approximately 30,000 barrels of fluid. As a result, the child well communications remained similar, but the parent-child communication was reduced by 51%. Some study takeaways. Using molecular chemical tracers, an operator in the scoop stack play was able to rapidly quantify the effects of different fracture communication mitigation strategies. This was accomplished with minimal cost, low risk, and without the need for large data sets or multiple trial and error efforts. The drilling and completion strategy was rapidly adapted for immediate improvements in estimated ultimate recovery and net profitability. This repaid the investment in the next incremental pad. The results of this tracer study justified additional tracer investigations into the effects of existing fault communications, alternate completions designs, and studies in other producing layers. That concludes the hydraulic fracturing case study, and now I'll hand the presentation over back to Sudipta for conclusions.
So thank you everyone for your attention. I know we've tried to cover an awful lot of information very quickly due to time constraints. The tracers have been used in the oil field now for decades. It really is a technology that continues to see innovation and prove and reprove itself to new generations of users as this rapid, cost-effective way to understand complicated well and reservoir problems. As we conclude, I hope that you take away that tracer technology is exceptionally versatile, but that an operator that has a clear vision for what they want from this diagnostic tool, working with an established data-driven partner, can really understand and unlock an understanding of their assets. That would be the envy of past engineers. With that, let us actually start taking some questions.
All right, thank you. We will now transition to the question and answer portion of our webcast. We've got a lot of great questions lined up, but you can continue to submit your questions in the Q&A box located on the bottom left corner of your screen. I'm going to go ahead and get started with our first question, and we've got just a few minutes left, so I'll remind our presenters that brevity is the cornerstone of wit. So, Sudipta, here's the first question. Would you say that liquid tracers are more effective to achieve quantification in well and particulate oil tracers are more helpful when trying to understand propped drainage radius, i.e. spacing tests or depletion effects?
That is a reasonable statement. So liquid chemical tracers, I tend to find are, yes, really the only choice when you're trying to understand quantifications from your lateral itself. When you're trying to look at intercommunication between wells, definitely either a polymer-enclosed or a particulate method gives you that understanding. It is harder, I think, again, to quantify the amount with those sort of release-based methods of applying tracer, but they definitely give you a much better understanding of overlapping stimulated reservoir volumes in a frac case or just overlapping drainage radiuses in a more conventional case.
Great, thank you for that. Now, Patrick, our next question is for you. Patrick, how can I use partitioning tracers to compare the effectiveness of each stage when we pump multiple hydraulic fractures?
Sorry, could you repeat the question, please?
Sure, of course. How can I use partitioning tracers to compare the effectiveness of each stage when we pump multiple hydraulic fractures?
Well, I think there's a couple of different things going on there as far as using partitioning tracers. Really, ideally, when you're looking at hydraulic fracturing and communication, we want to utilize tracers that are phase specific, that aren't partitioning. That way we can identify how much of the different phases are being produced. So either your oil, water, gas, and we can go ahead and quantify those recoveries in addition to how much completion fluid's been recovered from offset wells in wells that individual stages. So I hope that answers your question, because it seems to be a bit of a combination of looking at partitioning tracers and hydraulic fracture communication. And really we want to stick with phase-specific tracers.
If I could add to that, if you are limited only to partitioning tracers, then to achieve what you want to do, you really have to do a lot more sort of lab analysis ahead of time. So each stage that you're going to try and trace, you are presumably going to use a unique partitioning tracer to. So what becomes really important is understanding the degree to which your tracer is going to partition to different phases. So you're really going to need to do a lot of pre-work to basically see how much of your tracer is going to jump from, say, an oil phase to a water phase or an oil phase to a gas phase, and try and ensure that as you go across each frac stage that you try and minimize the difference in chemical behavior. So like this is a situation where, you know, if I use like a color as an analogy, if I use different shades of blue and purple indicating like very similar sort of partitioning behavior, maybe I can get a reasonable understanding of my quantitative flow. But if I have very different partitioning behavior, if you know, what I'm using in stage 1 really likes to jump into the water phase, what I'm using in stage 2 really doesn't, then any ability to quantify basically gets tossed out the window.
Excellent. Thank you for that response. Mona Lisa, this question is for you. In interwell tracing, how do you account for liquid tracer loss to formation when quantifying results?
Yeah, so what I understand from the question, like, so what we do is, like, we already have, before initiating a tracer study, we will have a particular mass calculated beforehand. Let's see, for example, in a particular study area or volume that I want to see, I would know that I'm injecting 10 kg of particular tracer A. And then when through an injector, it gets produced differently with the same tag tracer at different producers, I know that the amounts, or I can quantify the mass at different producers. So let's say if I have an injector I1 and there are like 3 producers, A, B, and C, I know out of the 10 kg, 1 has been produced from A, 2 has been produced from B, and 3 from C. So I know it is like 6 kg that I got until the end of my tracer study doing a mass balance. And how do we do that? We just simply take your production rate for water and multiply the tracer concentration over time, and that's how you do your mass balance. So we know we have injected 10 kg in our injector, and then we produce 1 kg, 2 kg, and 3 kg from A, B, C producers, and I know that 4 kg is lost in the reservoir somewhere. Either it is within the reservoir in the circulation system. To be, you know, if we continue the tracer study, there would not be a complete recovery and then 100%, but some would be lost in the reservoir, but then some would be, you know, always, there might be a possibility there's another producer which is not being sampled, and we also have tracer signals there. So we always have an account like this person, this 10 kg was injected and we recovered 6, and 4 is somewhere there, out there. So that's how we account for the loss, and through a mass balance. I hope it answers.
And again, proper selection of your tracer makes a big difference here because you want to minimize sources of loss. So if you've properly selected a tracer, then you're not going to see loss due to absorption into your reservoir rock. You're not going to see loss due to biodegradation from downhole bacteria. You're not going to see loss due to thermal degradation. Ideally, the only loss you should see is because it has just not been recovered due to diffusion in your reservoir volume. In those cases where you do have loss because of basically incomplete reservoir study, I mean, there are workarounds. But for interwell, a lot of the really fundamental work was done by a gentleman named Shook. And at the time that he was doing most of his work, thermal degradation was a big issue, where you would inject tracers, but you would know that as it's traveling through your reservoir, heat would slowly break down your tracers or cause it to precipitate out. And in those cases, you can actually add in a correction function, basically trying to describe that loss of tracer as sort of a decay curve and modify your mass balance accordingly. But in an ideal world, or in a world where you have the ability to really do a lot of pre-planning, you're going to pick a tracer where sources of loss are minimized.
All right, thank you for that. And now, unfortunately, in the interest of time, this will be our final question for the morning. And Patrick, this question is for you. In the current climate, it may not be possible to have third parties on site to install tracers. Do you offer a service where the operator can do this themselves?
Yeah, that's a great question. You know, in these times, reducing risk, headcount, and cost is important to accommodate. And you know, to be able to accommodate this, we've developed several different DIY type applications, do-it-yourself tracers, if you will, that are available for very different types of applications, both in the solid and in liquid form. So really, based on the goals and objectives, these may be the best option under the current environment. You know, as a global company, you know, depending on your location and government requirements, different applications will be available, and those have to be looked at kind of as at an individual basis. So there's many options available to accomplish goals and objectives that can fit that category.
All right. Well, thank you very much for that, Patrick. And so we come to the end of our presentation, and on behalf of World Oil, I would like to thank all of our attendees for participating in today's webcast. I'd also like to thank TracerCo for putting together this timely and informative presentation. And one final note, an on-demand version of this webcast will be made available in the coming days, and our attendees will receive a link to that via email. So if there was anything else you wanted to review again or study further, you'll be able to do that with that on-demand version. So with that, thank you all very much for attending. And
for those of you whose questions went unanswered, please feel free to email us. For the most part, our email address is our first name, period, last name @tracerco.com. We'd love to answer your questions offline.
Excellent. Yes, thank you for adding that. And so with that, please do feel free to email the presenters your questions. Thank you very much, and have a great day.